Guys, today we're doing the next section, 15.4 on double integrals and polar coordinates. Hopefully you guys have already seen the 10.3 section on how to do polar coordinates. Just as a refresher though, what we should have gleaned from that section is how to write Cartesian coordinates, so regular XY coordinates, in polar form. Okay, polar form, anything I give you guys is going to look like r theta. What the heck is that r and theta, you might ask? Well, if I wanted to sketch this out, my usual xy coordinate, instead of giving you this in terms of a position on the x-axis and a position on the y-axis, what I would do is tell you how far out we went from the origin, that's your r, and how far over we went from the positive x-axis, that's your theta. Okay, so that's what we did last time. What's the big punchline from that section? Why did I care? Well, I hinted at the very end of it that this might be able to help us with some of our trickier double integrals involving circular regions. So the big question that I want to answer is this: how do we rewrite Cartesian integrals in polar? Okay, so hopefully once we figure that out, we'll get a sense for how this is going to be able to help us, simplify those crazy looking integrals like the one that we saw last time. Okay, well, if I want to answer this question, the thing that I want to think about is this. Well, when we're doing double integrals, when we first introduced those, okay, usually I'm going to throw you guys something of this form, right? We've got my double integral symbol over here to suggest I'm going to be taking some sort of iterated integration type computation. I am specifying a region that I am integrating over, so pretty much everything I've thrown you guys is definite. I've got a function of x and y, which refers to this Cartesian system, and I've got this area differential on the end, okay, which, we've said a couple times before that this is usually rewritten as either dx dy or dy dx. Well, that means that there's three things for me to fix here, okay? I've got my bounds, and I've got my function, and I've got my differential, right? So the three pieces that I want to break this into are: I am going to want to fix my bounds. I'll say that one more time. I am going to want to fix my function, okay, that f of xy that I had, and I'm going to want to fix this differential that appears on the end. Right? Those are the three pieces that I am going to worry about: bounds, function, differential. Now, a couple comments on where we're at thus far. The bounds. I told you guys that we introduced polar coordinates for dealing with stuff in terms of these circular region. Well, for your bounds, I'll go ahead and make that note here. If you're on round regions, well, this is probably going to give me something that I'm dealing with polar intervals on. Okay, and we've discussed, tail end of last section, what does it look like if I graph some polar intervals? We've seen what those look like. So this is something that maybe we might have a hint on how to do. So that's well enough. Fixing my function. Well, if I think about that, last section we also did talk about converting to polar coordinates. We've mentioned that x should be the same exact thing as r cosine theta, and we've got that y should be the same exact thing as r sine theta, so that should be pretty straightforward. But this dA that's on the end, right? What do I do with that, right? dx dy or dy dx? I need to figure out some sort of way that I can port my differential over, because it's maybe, clear how to convert coordinates. Okay, I gave you guys the formulas for transitioning between the x and y and r and theta, but changes in x and changes in y, how do those correspond to changes in r and changes in theta? That's going to take a little bit more work to suss out, right? So these three bits here, okay, fixing my bounds, fixing my function, and fixing my differential, This guy on the end here, this is the one that we're going to need to think about, okay, to really nail down this transition, okay? Now, with that said, before I move on and actually tell you guys how to do this transition with dA and my new, polar coordinates, I did want to point something out. This idea where I've got this triplet of fixing my bounds and fixing my function and fixing my differential, this is actually sort of an idea that you've kind of seen before. Maybe not explicitly in the same manner that we're using it right now, but you have seen techniques where you do have to change your bounds and your function and your differential over. We did this in Calculus 1 and Calculus 2. If you saw U substitution there, you're changing all your x variables over to u. That was how you fixed your function. When you found a u, you had to find a du to fix your differential. If you were doing a definite u substitution integral, you would have to change your bounds over. Okay, so it's kind of a similar idea for u substitution. And when you did trig substitution in Calculus 2, trig substitution was basically a fancy version of u sub. Okay, so we still had to do kind of the same thing where you fix your function and your bounds and your differential. I'm pointing this out now because you guys are going to be seeing this a lot from here on out, so please get used to this idea of me saying that we have to fix this triplet of things, okay? We're going to have to do it here. We're going to have to be doing it time and time over again for the rest of the semester. But, at any rate, in this particular case, how do I fix my bounds and my function and my differential? This is the one that we don't know how to do yet. Okay, so let's think about how we rewrite that dA for polar. Well, for me to understand how to rewrite dA for polar, I have to think again about what this dA really means. Well, dA, this little d that's at the beginning of this thing, means that it's a differential, right? I keep saying that word. What the heck am I trying to imply by it? Well, differentials were things that allowed you to approximate incremental bits of change in whatever variable you're addressing. Now, A is supposed to imply area here, so I will go ahead and note that. This is my differential for area. So if I'm, dealing with some sort of incremental change in area, area's a two-dimensional thing. If I'm in my standard Cartesian coordinates, and let's say I give you some sort of itty-bitty incremental change in x and some sort of itty-bitty incremental change in y, well, these are actually standing in for, true change. That's what the triangles mean. But, your differential for area, if you have a incremental change in area here, it corresponds in Cartesian to you having taken some sort of change in x and some sort of change in y, right? We have got that your small changes in area are going to come from this guy. So this implies, if you're playing around with your differential approximations, okay, differential approximation, what this is going to give you is that your change in area is going to be dx dy or dy dx. We said that it doesn't necessarily matter too much which order we do the integration in, as long as we spell out the region appropriately, right? So that's what we're replacing my dA with, and kind of why. It's because any time that you've got some sort of incremental change in area, it was related to some sort of incremental change in x and y as well. Now, polar, on the other hand, how do we find these minuscule polar areas, though? Okay. If I've got some sort of minuscule change in area that results from changing around my polar coordinates, well, how did I get that? Well, my minuscule changes in area arise in a slightly different manner. Since we've got polar areas, remember we've got r theta coordinates, and if I'm changing an r around, r is really my distance from the origin. So if I'm at a constant distance from the origin, that really means that I lie on some sort of circle somewhere. I'm not going to draw the whole thing. But if I incrementally change my r, so if I, increase that just a little bit, this here is going to represent some sort of a change in my r. Okay, I increase my radius a little bit, I get a slightly bigger circle. Now, the other half of my coordinates for polar, we always give these in terms of r theta. Theta tells you how far off of the x-axis you are. So if I'm, some particular angle theta off, and I decide to incrementally change that, say I make my theta just a little bit bigger, well, this is really where I'm getting my change in theta. Okay, so here, this little region here, this box that's kind of at a tilt, this is going to be kind of the incremental area that we're inspecting. So this is what I want to relate to my change in r and to my change in theta. Now, the catch is I can't just take change in r and change in theta and multiply them out and call it good. Reason for that is this, maybe it kind of sort of looks like this thing is a box, and maybe it might be about like delta r wide, and delta theta is not really a length measurement, right? You can kind of see by the fact that, if I take something really, really close to the origin versus something that's maybe much further away from the origin, that's not a fixed length there. So I can't just multiply these two to get area. What can I do instead, right? So if I want my minuscule polar area, okay, I really want to ask myself, how do I find my area of this thing? Okay, right? How do I find my area of this? Because figuring out how that, delta A comes out is going to give me some sort of idea for how to get my differential approximation for dr and d theta instead of delta r and delta theta. Okay? Well, let's think about this. I'm going to start off not just with the little box itself, but I'm going to start with the area of the ring, right? Start with my area of my ring, because that's probably going to be, something that is a little bit more approachable than the current problem, right? If I start with my area of my ring, okay, that ring is coming about by, these are terrible circles, but that area of the ring is coming about by taking a difference of areas of circles, right? So I've basically got my area of my outer circle minus my area of my inner circle. Well, that's hopefully not too intimidating. Area of a circle is pi r squared. So I probably want to take pi times my outer radius. I'll call this r out for now, pi r squared. And then I'm going to subtract off the area of the inner circle. So minus pi r in squared. Okay. So that's my area of my ring, right? So this is just the ring. Now, the catch is we don't want the full ring, right? If I scroll back up a little bit, the thing that I was concerned with is just this stupid little box right here in the middle. So that's maybe just one tiny little fraction of the ring. Now, I phrased it that way on purpose. If I'm worried about the fraction of the ring that I have, well, what fraction of the whole am I really looking at? Well, this is where that delta theta comes in, okay? The area of the section that we want, right? So the area of, our desired box, and I'll put box in quotes here, it's not actually rectangular. We need to figure out what sort of fraction of the whole is our box, and then I need to take that fraction and then multiply it by this above area, right? So this area of the ring that we just noted above. Well, let's think about this. If I scroll up to look at this picture here, we've got this tiny little sliver of angle, but that's just a sliver out of the whole, 360 degrees, or we don't usually use degrees in this class. That's a tiny sliver of the 2 pi radians that it takes to go all the way around the circle. So what I'm going to do is use that, right? The fraction of the whole that our little box-like region is, again, I'll put this in quotes, it's not a box, is you take this delta theta, and that's just one sliver out of the whole 2 pi radians to go all the way around. Now, we already decided what the area of the ring was. We said that this was pi r out squared minus pi r in squared. I'm going to do some cancellations and some fancy algebra here to try to play around with this to get it in a simplified form. I said that I wanted us to figure out what this area of the box was because it was going to relate to our differential, and this looks like a hot mess. I'm not going to have you substitute something into an integral that looks like this. So what do I want you to substitute in? Well, let's tweak this a little bit. First off, you notice that everything inside of my parentheses has a pi attached, and I am dividing by a pi. So one thing I'm going to do is go ahead and make that cancellation, right? Get rid of all my pi's. The next thing that I'm going to go ahead and do, and it maybe seems a little bit counterintuitive to make this a longer expression, but I'm going to factor this out. What I mean by that is this. That r out squared minus r in squared, it's really a difference of squares. So what I could do is I could think about this thing as maybe, let's say that I view this as r out minus r in, and then I am going to multiply this by r out plus r in. Now, one of the reasons that I did that is this. If you focus on this little piece right here, my r out minus r in, that's me taking my outer radius and then subtracting off what my inner radius is. Now, I don't know about you guys, but that really sounds like a way that I can describe the change that happened in my radius, right? I'm telling you how much it took to get from the smaller one to the bigger one. So, a different way that I could express this, which is maybe more useful for us, is I can think about that guy as really just being a change in r. Now what this is going to leave me, and I'm going to shift some stuff around here, is I've still got this r out minus r in, and I haven't forgotten the fact that I was dividing by 2. Okay, that is still necessary here. I've still got this r out minus r in divided by 2. Now, a comment, plus, not minus, we already replaced that one. If I'm taking the sum of these things and then I'm dividing by 2, what it kind of looks like I'm doing is this. Here I've really got an average of my radii, right? Now, it's been a while since I've drawn the picture, so just for reference again, here's kind of what I'm looking at. Here's my r out, I guess, and here is my r in, okay, right here and right here. And this sector that I was trying to find was, the area of this thing right in the middle. Now, if I averaged my radii, this is going to give me something smack in the middle. So that will track, you know, all the way across here. What I'm going to go ahead and do is imagine that I have some sort of a point that's smack in the middle of my sector, right? Here, what I'll go ahead and do is I will let this point in the center of my sector be, I don't know, let's just call this R naught, theta naught, so that that little average point right there is my R naught. Well, that'll let me simplify my notation here so that that average turned into this R naught. Actually, I'll write this in order here. Let's call this delta theta delta R naught. Okay. Or maybe a bit more commonly to how you would expect to see this if you were actually doing an integral. I'm going to write this with just that R naught first so we know that it's not like part of a differential or a change estimate or something like that. And I'm going to follow this with a delta R and a delta theta. So this is what we've got. If I'm trying to compute the area of this little wedge in my figure here, I need to know what my radius is roundabouts where I'm trying to take the area, and I need to know, you know, what incremental change I had in R and what incremental change I had in theta. Hopefully this makes sense, because if you have a really, really small R, you're going to get a really, really small area compared to if you have a really, really big R, you're going to get a much larger area. You'll notice that I try to make these things about equally wide in the R direction and equally wide in the theta direction. One of them is much bigger than the other just because of its proximity with respect to the origin. Further away that you get from the origin, so the larger R naught is, the bigger that area chunk is. So all in all, what this really boils down to is this, and here's kind of the key takeaway if all this has been flying over your head. What this suggests is that this area differential, okay, the one that we've been trying to figure out how to write this entire time, my area differential, dA, well, I should be able to replace this not only with dx dy or dy dx, but I can also replace it with r dr d theta. Okay, so if we're dealing with polar coordinates, this is how we switch that up. Now, as far as formally writing this down, I'll go ahead and throw this in one piece here. If you're changing to a polar integral, these are kind of the assumptions that we're going with for our base model. You got a continuous function. Pretty much anything I throw you guys is going to fall under that hat. We're dealing with this polar region where R is stuck between A and B. You notice I'm making the restriction that we've got our best case scenario. We're trying to avoid negative R values. And I've also got that my angle is stuck between alpha and beta. Again, we're trying to shoot for best case scenario. We want to make sure that our region isn't overlapping on itself. You know, theta, if you specify an interval of theta that's longer than 2 pi units, you're going to start wrapping back over and counting your region over twice. We don't want to do that, so I've got a restriction on my beta minus alpha here. Now, if you meet those restrictions, this is how you end up rewriting your integral. And it lines up with exactly what I mentioned before. We still have to fix my bounds. Okay, these have to be things that refer to r and theta. We still have to fix my function. You have to get rid of all those x's and y's. And you still have to fix your differential. We just said that the area differential is going to be equal to r dr d theta. So we have to make sure that we've got that conversion straight, right? So again, I will reiterate, if you're going to change to a polar integral, you have to fix your bounds, you have to fix your function, and you also have to fix your differential, right? Fix these 3 things, okay? All 3 of them. If you want to see this in practice, I'm going to go ahead and try the example that we saw was really, really horrible last class. That x squared plus y squared integral, the one with the trig substitution and the trig integrals and all the identities, and it took like 2 pages to do, okay, because we were working on the unit disk centered at the origin. Let's try this, but in polar, right? So need to worry about my bounds, need to worry about my function, need to worry about my differential. Now, again, unit disk, centered at the origin. This is my region that I wanted to integrate over. Well, this region in polar is actually super, super nice, right? Reason that I say that is if you're worried about bounds on r and if you're worried about bounds on theta, these are just intervals. I'm not dealing with like weird square root functions or anything like that. You'll notice since this is the unit disk, and it does go all the way up to the origin, the distance from the origin of the various points that are inside of this disk, well, if you're at the origin, you are 0 units away from the origin. And if you are further away, let's say you are all the way out on the boundary of this disk, if you're on the boundary of this unit disk, the furthest away you get from the origin is 1 unit. So r has to be stuck between 0 and 1. On the other hand, if you're worried about your bounds on theta, I can ask myself, in this region, what angles are permissible for me to hit? Well, if you start at the angle 0, you'll notice that we sweep through angles all the way around. So we go all, 2 pi radians all the way around the origin. That means that my bounds on theta are going to range from 0 to 2 pi. Okay? So that'll help me figure out my bounds. As far as figuring out my function goes, I will go ahead and make note. We do have to recall that x equals r cosine theta. That was our conversion factor for x, and y equals r sine theta. That was our conversion factor for y. And I also have to recall that differential conversion that I gave you guys, dA was supposed to be r d theta. So let's see if I can put every single one of these things together here, okay? I'll worry about writing my function first. Okay, we said x squared, that means this is really r cosine theta squared, plus y squared, that's really r sine theta squared. So I have fixed my function, okay? That part's taken care of. Next thing that I'm going to go ahead and do right now is fix my differential. We have said that dA is supposed to be r d theta. Well, I'm just going to throw that on the end. So differential fixed. Last thing that I need to do is fix my bounds, and you'll see the reason that I did this last is I wanted to make sure that everything matched up. I've written this so that r was my inner bound and theta was my outer bound. Well, r has bounds 0 to 1 and theta has bounds 0 to 2 pi. So now we can worry about trying to clean up this integral from here. Okay, I'm going to scroll down to give myself some room to work. I will make the comment, if you do r dr d theta or if you do r d theta dr, it's really the same thing. Just make sure, again, that you're consistent with matching your bounds up. If it does behoove you to do it in the other order, or if your problem would be nicer for you to do it in the order, you are welcome to set it up the other way because, we've seen Fubini's theorem. You got constant bounds. It doesn't matter. But at any rate, I don't want to integrate it like this. I'm going to clean this thing up a little bit. Namely, I can actually take these squares here. You'll see that I have got, if I clean this up, r squared cosine squared theta plus r squared sine squared theta. I'm going to hang on to this r for the moment here. And then some further cleanup that I can do is this. Maybe you might have seen this coming, but if I pull an r squared out of this piece here, what that leaves me with is a cosine squared theta plus a sine squared theta. Okay, and at this point, you should see where I was going with that piece. At the very least, this cosine squared plus sine squared bit, that's all just going to cancel, so I'm going to rewrite that. That turns into 1, right? So ultimately, what that simplifies to is just, we've got an r squared times an r. I am now worried about integrating r cubed dr d theta. My antiderivative here should be taken with respect to r first, so that means that my first antiderivative is going to be r to the 4th over 4, evaluated between r equals 0 and r equals 1. Well, that's not too bad. If you plug in 1, the top bound, you're going to get, well, 1/4. If you plug in 0, you get 0. So you're not subtracting anything off. And that means that we're really just worried about integrating 1/4 with respect to theta. Okay? Antiderivative of a constant, you're just going to slap the variable on the end and then evaluate it at the bounds. So here, if I plug in my top bound, I've got 2 pi over 4. Again, if I plug in the bottom bound, I'm subtracting off 0. So not much to subtract off. And that means that my end result here is pi over 2. Now, a comment, if you did bother to look at all the awful scratch work that I did, this is the exact same result, but we got this a lot faster, and it's a lot less painful to do this, the simplification, right? So we maybe did have to make use of a Pythagorean trig identity right about here. Okay, cosine squared theta plus sine squared theta is 1. But aside from that, everything else cleaned up very nicely, right? So pretty painless integral that didn't involve any like trig substitution or like weird obscure half angle identities or things like that. And it came out really nice. Comment that I will make before I run, okay, and this is kind of a useful note to make. The reason that I did sort of write this out in this manner without simplifying a lot faster, I'm going to draw attention to this stretch here, okay, in the problem, the r squared cosine theta plus r squared sine squared theta, okay, how that reduced to r squared. I will point out that where we substituted that in came from this line above, and where we substituted that in came from this guy. Okay, so shortcut trick for you guys to glean from this. Okay, so kind of a shortcut, and you will expect to see this in probably a lot of problems. Any time that you've got x squared plus y squared, you're ultimately going to replace this guy with r squared. Okay? And hopefully, you know, if you think about the picture, this makes sense because we're really just doing Pythagorean theorem on that, right? But, again, same idea, fix your bounds, fix your function, fix your differential. If we've got a round region, this is going to go a lot faster.